Everybody. So in our series of lectures on basic electronics, learning by doing, let us move on to the next lecture. Before we do, as usual, we will look at topics that we learnt during the previous lecture. You might recall that we discussed the basic principle of integrated circuits, how integrated circuits are developed, formed, and then operational amplifiers, some of the characteristics of an ideal and a typical operational amplifier, and the concept of feedback, and we also derived an expression for the gain of an amplifier with negative feedback, which is one of the very important aspects of electronics. Now let us, before we move on to the next topic, it will be good to recall the typical characteristics of the operational amplifier once more, both the ideal and a typical op amp, which is a very popular one, 741. So if you look at the open loop gain, which is called AOL, the symbol, the screen, the ideal op amp has got infinite gain, very large gain, whereas a typical 741 has got a gain of 100,000, which also is a very large number. If you look at the unity gain frequency, you can, that means it corresponds to a bandwidth with gain 1, you would find for an ideal operation amplifier it is again infinity, and for 741 it is 1 megahertz, 10 to the power of 6 hertz. So from 0 to 10 to the power of 6 hertz, the amplifier will have reasonably constant gain of about 1. The input resistance, if I look at it, for an ideal op amp it is again infinite and infinite, and for an operation amplifier, typical operation amplifier 741, it is about 2 megohms typically. Similarly, output resistance is 0 for an ideal op amp and about 75 ohms are around that for a typical operational amplifier which you buy from the market. So you can see most of the numbers are really very close between the ideal and the actual op amp. There are other characteristics that also we saw, we did not discuss in detail about them, we will perhaps do it in the course of next couple of lectures. Input bias current, which also should be 0, and typically it is about 80 nanoamperes. Input offset current, that is also 0 ideally, but it is about 20 nanoamperes, a small value, and input offset voltage is 0, but it is about 2 millivolt for typical op amp. And the common mode rejection ratio, we discussed this in some detail when we discussed about differential amplifiers, and the common mode rejection ratio is an ability to distinguish between common signals and differential signals at the input of any difference amplifier. The op amp input stage being a difference amplifier, we have to worry about the common mode rejection ratio of that, and ideally it should be very large, CMRR infinity, and in an actual case it should be 90 dB, and I am sure you can immediately recognize 90 dB should be more than about 10,000, more than 10,000 is the voltage gain for differential input to common mode input. The gain AD by AC is what is called a CMRR, and that is nearly 10,000, 10 power 4, 10,000 and large. We also saw in the previous lecture about negative feedback, how negative feedback is very important for control applications, and in an amplifier when we say negative feedback, what we mean by that? We take a portion of the output voltage and feed it back at the input, and when we feed it back, we try to feed it back at opposing phase, not in phase with the input signal, and therefore it is called a negative feedback. So this negative feedback, if you recall, we derived an expression for the gain with negative feedback, V output by V input, V output by V input, the negative feedback is inside the amplifier, and therefore that new gain I call that AF, which is the gain with feedback. So this is related to the intrinsic gain A of the amplifier by this expression which we derived last time also. I have shown here the mathematical steps. So, AF, the gain with feedback, is equal to the gain without feedback, A divided by 1 plus A beta, where beta is called the feedback ratio. What is the proportion of the output voltage which is given at the input? This is called feedback ratio. It is usually less than 1, and so A beta will be a very large number, right. When if you, in an ideal case, when you have A tending to infinity, limit A tending to infinity, this expression will become 1 by beta, that I also explained to you last time. Limit A tending to infinity, this will reduce to 1 by beta, and that means beta is in the hands of the user of the op amp. He can choose proper network for the feedback, by which you will be able to completely decide the property or the behavior of the amplifier by using the external resistors, capacitors. That is why we want to have as high a gain as possible for the operational amplifier. That is why we want to have the gain of the amplifier to be around 100,000 or more. In the ideal case, it is infinity, because then it becomes very convenient. The characteristics of the op amp itself is not the deciding factor, but the external resistors, components that I use for the feedback network, I can control, and thereby I can control the behavior of the amplifier. This is a very important concept, and you would see in this lecture and the next one also I will keep stressing about this point, and I will show you how this comes about. So, let us look at some of the important thing. I generally mentioned about feedback, negative feedback. That means a portion of the output is connected in phase opposition to the input. That does not tell you what is it that I sense at the output and what is it that I give at the input. I sense something from the output, and a portion of it I give at the input. Now you have several choices. For example, the output, I can sense the voltage, the output voltage, and feed it back as also a portion of a voltage at the input. So, I can sense a voltage and give a voltage at the input, a fraction of that voltage in phase opposition. The other way, I can sense the voltage and give it as a current at the input, or I can sense the current at the output and give it as a voltage, or vice versa. So, you can see there are 4 different ways in which I can take a portion of the output and give it at the input. These 4 different configurations of feedback is what is very important for us to learn about in this case, and I have shown you in this picture on the screen the 4 different configurations. For example, in the first one, you sense the voltage because you are connecting them, your beta, the feedback network, you connect in parallel to the output points, and therefore you are actually sensing the voltage at the output point. So, you sense the voltage and you give also a voltage here in series with the input terminals of the amplifier. Therefore, voltage series is what some people call this type of a feedback, voltage sensed and given in series. If you look at the second picture, you can see the voltage is again taken here because it is taken in parallel at the output, and it is also given in parallel at the input terminals. Therefore, the input voltage at the terminals of the amplifier and the feedback voltage are actually connected in parallel. The 2 networks are in parallel. Therefore, this is a shunt. So, voltage given as a shunt at the input. So, this is a second configuration. Similarly, you can sense the current in series. If I put something in series, the same output current will have to flow through the beta network also, and therefore, this is a series connection, whereas in the other case it is a parallel connection. You connect in parallel to the output impedance of the amplifier, the network also in parallel, and therefore, this is a series connection. If I connect a series, then the current is a constant in a series circuit, voltage is constant in a parallel circuit, we have seen that also. So, this series current generates a voltage, and that voltage is fed back at the input. So, this is called current connected as a voltage in series, and the other one you sense again the current and give it as a in parallel, therefore in shunt. So, current shunt feedback. So, you have 4 different types of feedback configurations possible for a given amplifier, voltage amplifier like an op amp. So, in an op amp we can implement these 4 different types of feedback circuits. All of them correspond to negative feedback, and all of them will correspond to a very good nice circuit which is very useful for several applications. We will see it now. So, what I am now going to do is take one by one each of these feedback configurations and try to explain to you what is the consequence of this feedback configuration on the effective output resistance of the amplifier and the effective input resistance of the amplifier. So, you have to remember that every amplifier can be drawn as an equivalent circuit with an input resistance Ri and an output resistance R0 in series with a voltage source which is actually AOL times V epsilon. This is a voltage source which is taking care of the gain factor of the amplifier, which is in this case the open loop gain. I have not shown this because I am trying to look at in terms of the Thevenin's equivalent circuit, and therefore the voltage source is short here, and what you see here is only the output impedance R0. Now I take a equivalent network of resistance here at the feedback network. I can always look at it as some resistance R of O, which is the feedback network resistance of the feedback network, and I am sensing the voltage in parallel. Therefore the same voltage V0 is also applied across this R of O, and by some potential divider or something I take an effective voltage at the output, and that output I give in this configuration with a phase inversion. You can see this is plus minus, this is plus minus. So whatever is the input voltage, that input voltage, the entire voltage will not be applied here because they are connected in series. You can see this is like connecting two batteries in series. So VE epsilon plus VF is what is equal to V in. Therefore what is V epsilon, which is the voltage exactly connected at the input, is going to be V in minus this VF. Therefore already you can see because of the feedback the input voltage is decreased. V in is larger than V epsilon. That means all the input voltage that you connect is not applied at the input terminals of the amplifier op amp, because some has been neutralized by the feedback voltage Vf that I have taken. So voltage is sensed in parallel at the output. Because of that, now if this is the RL, which is the load resistance at the end of the amplifier, this load can be anything, it can be a loudspeaker or it can be something which you want to drive after amplification. Now if I look from that end, the output resistance end, and look into the amplifier, what you would observe? You would observe two different resistors coming in parallel. One is the output resistance of the amplifier, and the other one is the output resistance as seen as a Thevenin's resistance of the beta, the network that you have connected for the feedback. So these two resistors, when you connect in parallel, you know what is going to happen. The effective resistance is going to be the parallel value of these two resistors. You know the parallel combination of two resistors is always less than the smallest in that group. So you can never get R0, you will always get a value which is less than R0, effective resistance. So the effect of connecting in parallel a feedback network is to reduce the output impedance. That is what I want you to understand. When I connect any network in parallel to the input, you will always get a effective resistance at the output reduced. Okay. Now let us see what happens. So RO effective is parallel value of RO and RFO, which RFO is the feedback network. Then RO effective is always less than RO, the output resistance of the amplifier. Similarly, if you look at the input, voltage is connected in series with the input signal, and therefore what I get will be less than the actual applied input, because some feedback voltage will reduce some of the magnitude. So Ri effective, the input resistance, is the sum of this plus this, they are coming in series. Therefore the total resistance will be the sum of the input resistance of the amplifier and the input resistance of the network together. So what is going to happen? The effective resistance because of the feedback will always be larger than Ri alone without feedback. So the effect of feedback network at the output resistance when I sense voltage in parallel at the output is to reduce the output resistance. the effect of connecting the voltage in series at the input is to increase the input resistance. So, if an amplifier has got increased input resistance and decreased output resistance, what will be the type of an amplifier? For an ideal voltage amplifier, the input impedance should be very large. We have seen it number of times. The input impedance of an ideal voltage source should be very large, so that the entire signal is applied across the amplifier, very small fraction is dropped inside the source resistance. Therefore, if I have a very large input resistance due to this configuration, the input will have to be a voltage, and therefore I connect a voltage here, and what I get at the output is a decrease in the resistance due to feedback output resistance. Whenever there is a decrease, that means it becomes much closer to an ideal voltage source, and therefore the output will be able to drive any kind of load, any magnitude of the load. That means this has to be a voltage source. Only a voltage source will have a least internal resistance, and therefore you have the reduction in resistance due to this configuration makes the output more and more closer to a voltage source, and the feedback that is given at the input makes the input higher resistance, input resistance higher, and therefore that makes it much more useful as a voltage amplifier. Therefore, the input is a voltage, output is also a voltage. The output voltage is controlled by the input. Therefore, this configuration is called voltage controlled voltage source. The output is a voltage source because the output impedance is decreased due to the feedback, and therefore it is controlled by the input voltage. Therefore, this configuration is called voltage controlled voltage source by some people. Okay. In the same way, we can argue for each of the configurations that I showed you, 4 different configurations. For example, here I have, again sensing is done in parallel, voltage sensed in parallel, and therefore the effective resistance is the parallel value of RO and RFO, which is in principle effectively to reduce the output impedance of this combination, and therefore the output resistance is reduced here. And if you look at the input, it is different from the previous thing. Here I am giving it in shunt, I am actually connecting the voltage in parallel to the input voltage of the terminals of the amplifier. So when I have 2 resistors in parallel, you know the effective resistance is going to be small. So it is no more a voltage input, because if it is a voltage input, I must have large input resistance, then only it can be a voltage input. Now the effect of this feedback is to reduce the input resistance, and therefore the input will have to be a current. It is no more V in, it has to be I in. So the input is going to be a current, the output resistance is decreased, therefore the output is going to be still a voltage source, and therefore it is a current controlled voltage source. That is what we get when I give a feedback of this nature, and this is also called incidentally current to voltage converter. You would find we can get a very nice current to voltage converter by making this type of a feedback configuration using our op amp at a later stage. Now let us move on to the next circuit. Here you see here the voltage is actually not sensed. You will sense the voltage when you take the output in parallel, but you are taking the output in series, therefore you are actually sensing the IO, the output current is being sensed here. And if you sense the output current, you are connecting it in series to the output, and therefore the effective output impedance is increased, as you can see here. This R0 and RFO will come in series, therefore the effective resistance is larger than RO alone. Though due to feedback, the output impedance is increased. If an output impedance is increased, then the output should be a current source, because only for a current source the internal resistance is very high. If internal resistance of this amplifier at the output is having a higher resistance, that means it is becoming more a current source. If you look at the input, it is very similar to the first configuration we saw. We are giving the feedback voltage in series with the terminals, and therefore the effect is to reduce the effective input voltage connected to the amplifier, and therefore this will increase the effective input resistance, because here also it is coming in series, and therefore when I connect 2 resistors in series, the effective resistance should be larger. and therefore resistance is increased at the inputs, resistance is also increased at the output. The increase in resistance makes sure that what we apply will be a voltage, the increased resistance at the output shows that it has to be a current which is being driven at the output through the load, and therefore this is a voltage to current converter. It is basically the circuit becomes a voltage to current converter, or in another way you can call it as a voltage controlled current source. The current source will be controlled by whatever voltage that you connect here. So this becomes a voltage controlled current source, which is the third configuration. Now we come to the last configuration, the fourth configuration, where you see the feedback voltage is to be obtained by sensing the output in series, and therefore again it is going to be increased resistance at the output stage, and therefore it has to be a current source at the output. At the input I again connect it in parallel to the input terminal, and therefore the effective resistance is the parallel value of Ri and Rfi, which is always small, therefore effective input resistance is decreased. When the effective input resistance is decreased, then it has to be the current which should be driving the input rather than the voltage. Therefore this is a current input here, and you also get a current output here because the output impedance is also increased. So this is a current amplifier. You give some current here, you get a higher current at the output, so it becomes a current amplifier, and it is also called current controlled current source. The output current source is controlled by the input current that you drive through the input terminals, and therefore this feedback leads to a circuit which is a current controlled current source. Now having seen all the four different configurations, I have put them in the form of a table to show you in a nutshell how it is all. For example, in the first configuration it was the voltage at the input, you also got a voltage at the output because it was closer to a voltage source due to the feedback, and it is called a voltage controlled voltage source. Ideally a voltage controlled voltage source should have infinite resistance at the input, it should have 0 resistance at the output. In our case the input resistance was increased because of the series connection of the feedback, and the output voltage is decreased because we are taking that in parallel to the feedback network. So this is a V to V converter. In the second circuit you have a parallel connection, and therefore the input resistance is reduced, and therefore it becomes a current drive, and at the output is again the voltage because you are sensing it in parallel, and therefore it is a current controlled voltage source, and an ideal current controlled voltage source should have 0 input resistance and 0 output resistance, and it becomes a I to V converter. The third circuit is a V at the input, I at the output, it becomes a voltage controlled input source, and it will have infinite resistance at the input corresponding to voltage, and it will have an infinite resistance at the output corresponding to a current source, and therefore it becomes a voltage to current converter or V to I circuit. The last one is basically current controlled current source and ICIS, and it will have high input 0 input impedance and very high output impedance, and it becomes a current controlled current source. Right. In an actual case, when we discuss with a normal op amp these four configurations I would like to discuss, then you would find each one of them will turn out to be a very nice amplifier, almost an ideal circuit. First one will be an voltage amplifier, second one will be a trans resistance amplifier because the transfer function has got dimensions of resistance. Output voltage by input current gives me resistance, therefore this is a trans resistance amplifier. And the third circuit is going to be a conductance. I output divided by V in, voltage by current is resistance, current by voltage is conductance, therefore this is a 1 by R value I will get for I out by V in, which I call GM, and this is a transconductance amplifier, which is also very useful in different applications. And the last one is a current amplifier, and the ratio appears to be the same as what you get in the first case for the voltage amplifier, 1 plus R1 by R2. We will take different configurations, I will explain to you what is this R1 R2, where from it comes, but this is in general the four different circuits that you get from a single op amp by simply connecting 1 or 2 resistors in the feedback network. So, that is the greatest advantage, and you can see these voltage amplifier, transconductance amplifier, transresistance amplifier, current amplifier are almost very close to an ideal current source, current voltage, current amplifier, voltage current source, etc., because of the very good characteristics of the op amp in the integrated circuit form. That is why we discuss about that in detail. So, having done that background on the negative feedback, how different configurations can be connected and all that, let us focus on one of the op amp which is very popular, which is very easy and not very expensive, it is very cheap, you can buy in the market for about 10 rupees or so, and therefore this is the 741 operational amplifier. In fact, it is what in 1965 a company called Fairchild Semiconductor introduced the MUA 709 as their first operational amplifier, which was very widely used, but it had several disadvantages in terms of frequency compensation and all that, and therefore they brought out a more improved design of the same, and which they called MUA 741, and it is very easy and inexpensive to use, and therefore this has become a great success. Many people use this for different, you have hundreds of different types of operational amplifier to be used at different situations. So, we will have look at that at some stage. Now, if you look at the 741 itself, it has got different specification. For example, you can buy a 741, you can also buy a 741C, you would find 741C will be cheaper than 741. 741E, 741N, etc. These C, E, N have got some meaning with reference to the temperature ranges for which the operational amplifier can be conveniently operated, or on the basis of the noise levels and things like that. So, for example, 741C is a commercial operational amplifier, and therefore they will be suitable for only a small range of temperatures from 0 to 75 degrees centigrade and all that. If you go for a military specification, for example, then the same op amp will have to be manufactured for much stringent variations, that means much larger range of temperature variation from minus 50 degrees to plus 120 degree and things like that, and that becomes a military specification, and so it will automatically be more expensive because more care has to be put in the design of such op amps, so they become more expensive. But most of the time we will be discussing only the 741C, which is the cheap inexpensive operational amplifier easily available in the local market. You also have the same 741 manufactured by different manufacturers. Even though it was a Fairchild who started the first manufacturing of 741, many other people also started manufacturing the same operational amplifier almost with identical characteristics. For example, LM741 is actually op amp manufactured and commercialized by National Semiconductors. MC741 is a operational amplifier manufactured by Motorola company, and SN72741 is again a operational amplifier with the 741 again coming there, manufactured by Texas Instruments. Like that, there are different types of manufacturers, device manufacturers who manufacture, but all of them will have almost typical similar characteristics. So, people normally leave out this specification of the manufacturer, LM or MUA or MC, and they only specify 741. So, when I say 741, it could be from any manufacturer, it should have very similar characteristics. Okay, now having looked at the operational amplifier, let us now take one simple configuration of the operational amplifier. You can see you have this symbol of an operational amplifier. We normally do not show the dual supply, which I already explained to you in the previous lecture, corresponding to V plus and V minus, and you have the input signal connected to the plus, and there is a feedback that is given here. The feedback is a very simple configuration here. I just put a potential divider at the output R1 by R1 R2 and take the midpoint and connect it to the input. So, what I have effectively done is I have divided the output voltage into two parts, one across R1 and one across R2, and the voltage developed across R2 is applied in series with the input voltage, you can see in phase opposition, and therefore what you can get here will be a reduced voltage. That is the effect of feedback we have already discussed. and therefore what is this V2 or Vf, which we normally call Vf, is nothing but R2 divided by R1 plus R2 times V output. This is the RL, this is the V output. So you have taken that by sensing the output voltage, and therefore this is the feedback that you are giving. The most of the op amps have very large gain, extremely large gain, and very high input impedance Rin, and very low output impedance even without any feedback. For example, the 741C has a 100,000, I already gave you the typical table. R input is about 2 mega ohm and R output is 75 ohm. But now what is going to happen with the feedback, we will try to understand. So what you have here is the feedback voltage Vf or V2 in this case is R2 divided by R1 plus R2 times V output, and this R2 divided by R1 plus R2 is effectively the beta that we represented in our other circuits. We always said the feedback ratio here is beta, it is always less than 1, you can see. So V2 is beta times V out, right. We have assumed R2 and R1 only are existing, all the other things are not existing. You have an input resistance here, etc. Therefore there is an assumption here, and the assumption is that R input of the amplifier is very much larger than R2, and therefore it is the R2 which decides everything when they come in parallel. So this is also true most of the times. Otherwise you have to use a very rigorous expression for beta, which is R2 parallel Rin divided by R1 plus R2 parallel Rin to take care of the parallel value of R2 and Rin, right. So the error voltage to the amplifier, what I mean by error voltage is the actual voltage or the difference in voltage between the input voltage and the feedback voltage is what I call error voltage, and which is the exact voltage which is applied across the input terminals of the operational amplifier circuit. So V epsilon, I call that V epsilon, is nothing but V1 minus V2. We will go back and look at the V1 minus V2 is what I have here. So V1 minus V2 is, because it is negative feedback, it is minus V2. So V1 minus V2 is V epsilon, and that V1 is V input itself. V1 is basically the input voltage coming from the source. V2 is beta times V output, because it is a feedback voltage. So if I now substitute that, V output is equal to A times V epsilon, because the A is the open loop gain without any feedback, that will only amplify the voltage applied across its input terminals, which is V epsilon, we know that. So A times V epsilon is the output voltage, and instead of V epsilon we can write that is nothing but V input minus beta times V output, just now we saw, and therefore when you rearrange you find V output by V in A by 1 plus A beta, which is again the same circuit, same equation we got previously for any feedback, negative feedback amplifier. Okay, the product A beta is actually called the loop gain. For a non-inverting voltage feedback, this is a non-inverting voltage feedback to be affected, the designer must deliberately make the loop gain very much larger than 1, which is also true in our case, because A is going to be 100,000, beta is going to be maybe 0.5 or something, whatever it is, the number becomes very large, and therefore A beta is very large compared to 1, and therefore V output Vn, then it will become almost equal to 1 by beta, and beta is this case, you know, because we have used a simple potential divider, beta is R2 divided by R1 plus R2, and 1 by beta is the reverse of this, inverse of this, which is R1 plus R2 by R2, which can be rewritten as 1 plus R1 by R2. So this is 1 by beta, and this is the V output by V in, which we call the gain of the effective amplifier with feedback. So the amplifier gain with feedback is 1 plus R1 by R2, and you can see this is independent of A, the gain of the operational amplifier. This is the greatest advantage that we get, and R1 and R2 are the two resistors that we select in the lab depending upon the convenience, and therefore we can very easily change this and change the gain of the amplifier. So it becomes very convenient to increase or decrease the gain by simply changing two resistors R1 and R2 by using a very effective negative feedback configuration that we discussed. So that is the advantage of this. You also should recognize that people tend to write circuits in different ways show in different ways, but you would find you must be able to recognize, but they are of the same configuration. For example, these two circuits that I have shown on the screen appears as though they are two different circuits, but if you carefully observe, they are two identical circuits. You can see that the negative end is actually used for the feedback R2 and the R1 is connected to ground. Therefore, this is R2 plus R1 which is connected in the feedback loop, and that is connected to the negative point. Therefore, there is a negative feedback. The same thing, the way we showed just now, is R1 R2 put at the output as a potential divider, and the middle point is connected to V minus. So this and this are exactly identical. We have only interchanged the amplifier, flipped the amplifier about an horizontal axis by 180 degrees. So this is V in, here also the V in is connected to the plus terminal, here also the plus terminal, and the output voltage is measured across the output terminal of the amplifier. So these two configurations are identical. In books you would find some people show it like this, some people do it like this. It does not matter as long as they have given the negative feedback correctly and they were applying the input at the plus terminal and measuring the output corresponding to the output terminal. Right. Having seen that, let us just quickly take a simple example of a 741C which has got 100,000 gain. What is the closed loop gain? If V in is equal to 1 millivolt, what do the output error voltage equal? So in this case, the resistors values are given. It is 2 kilo ohm and 98 kilo ohm. So beta will be R1 is 2 kilo ohm, R2 is 98 kilo ohm. So T kilo ohm by 100 kilo ohms, that is equal to 0.02, that is a beta factor. So the smaller the beta, 1 by beta will be much larger, it will be 50. So the closed loop gain is 1 by beta, and that is around 50 for this circuit. That means the closed loop gain is 100,000 A divided by plus 1 plus A beta, which is also 49.975, very close to 50. And therefore you see, whatever way, whichever expression you use, ultimately the correct number comes out. So therefore we say 1 by beta is a good enough approximation for the closed loop voltage of an amplifier that uses non-inverting voltage feedback. And this is called a non-inverting voltage amplifier because, as you can see, the input is given to plus terminal, and between the output and the input there is no phase difference. Therefore the output will be in phase to the input, and therefore it is called a non-inverting amplifier. If I have to give to the negative terminal of the input for the op amp, there will be a phase difference between the input and output. In this case there is no phase difference, therefore it is called non-inverting amplifier. A non-inverting amplifier is almost close to an ideal voltage amplifier. So if V in is equal to 1 millivolt, the output voltage is gain, closed loop gain multiplied by V in, 50 multiplied 1 millivolt, you get 50 millivolt. And so what is the voltage that is exactly applied at the input? This is 50 millivolts is output voltage. So if I divide that by 100,000, I will get the V epsilon, the voltage which is exactly applied at the input terminals of the op amp. That is found to be 0.5 microvolt, you can see that. So it is a very small voltage that is only applied out of the 1 millivolt, there is only 0.5 microvolt applied across the input terminals. So the same configuration is shown here to bring about an idea to you that this not only, even though the gain has decreased from 100,000 to 50 in the previous example, for example, typically, but you do not have to worry. I already mentioned to you, this decrease in gain comes out as an increase in features corresponding to a good amplifier like the input resistance, output resistance, bandwidth, distortion, etc. Therefore what it is amounting to is that the gain of the feedback, gain of the amplifier becomes something like a deposit in a bank with which you can take risks and buy different things in the market without any worry, because you have a lot of credit on your bank. You can go and do several things boldly, take bold steps financially. In the same way, when you have a very large open loop gain, then you have by sacrificing that large gain by some factors, you will be increasing the other features outside. That is what I wanted to show you. For example, the input resistance with closed loop gain will become much larger than the input resistance without feedback. The output resistance will become much smaller than the output resistance without feedback, etc. Now, how do you show that? I hope you can remember, V input is V epsilon plus beta V output, that together only is that, therefore V epsilon is V in minus beta V output, that is what we already saw. So, V in is V epsilon plus A beta V epsilon, because V output is A times V epsilon, that is equal to 1 plus A beta V epsilon. Now, V epsilon is actually responsible for sending an I in through the R in, the input resistance. So, V in is 1 plus A beta times I in into R in, V epsilon I can write it in that way, where R in is the input resistance, and so V in by I in is equal to 1 plus A beta into R in, where R in is the input resistance of the amplifier op amp. So, V in by I in is that new input resistance. I apply from my source V in and it results in a current I in. This current is now a reduced current because of the feedback voltage. Therefore, V in by I in should be much larger than what it was without feedback. That is exactly what you are getting at the right side. You can see the input resistance which was there before is multiplied by a very large factor, which is 1 plus A beta, the loop gain. So, the A beta is a very large number compared to 1, therefore, it is multiplied by a very large number, and therefore, the effect of feedback is to increase the input resistance by several orders of magnitude, 1 or 2 orders of magnitude. So, the ratio output resistance R in, this I call R in CL, CL means closed loop. So, input resistance with closed loop is equal to 1 plus A beta R in. So, you find the input resistance is increased by a factor which is 1 plus A beta, that is the factor by which the gain was decreased. The feedback gain is A by 1 plus A beta, it is decreased by 1 plus A beta times, and here it is increased by 1 plus A beta times. That is why we still go for negative feedback, even though it reduces the gain, it improves the input resistance. Similarly, it improves the output resistance also. It can be shown R output with closed loop will be R output by 1 plus A beta. That means output resistance is still reduced by this factor 1 plus A beta. The nonlinear distortions which are there due to non-ideal conditions of the operation amplifier, or any amplifier for that matter. So, every amplifier will have some contribution to this. So, V output is A times V epsilon, which is actual output gain, plus some unwanted distortion that has come about due to the amplifier. If I give feedback, that part of the distortion also will be fed back, that distortion also will be reduced in effect, and therefore, the output voltage will therefore give a value which is A by 1 plus A beta times V in, which is due to the gain factor AF plus V distortion divided by 1 plus A beta. That means, it is a reduced distortion now, and the reduction factor is again 1 plus A beta, which is a number which we already met. So, you find the effect of feedback is also to reduce the distortion. Right. Now, having seen that, let us try to look at a simple simulation of the circuit. So, on the screen you see there is a breadboard, and you have a dual supply here. You have a voltage source which has got millivolts or volts input, and you have a multimeter here. You have to connect them, and the circuit is shown at the right bottom leftmost area corner. This is a circuit, this is a non-inverting amplifier with the signal source shown here, voltage source shown here. So, if you want to try, let us try a manual scheme. So, then you take the op amp and build the circuit. So, you put it in the corresponding gap. For example, I take it and put it where the hand shows, and now the other resistor is also taken and connected. So, we can connect the rest of the wiring. So, it will show you where the connection is done. Now, I am connecting the minus V minus terminal, the ground terminal, now the ground terminal, and now completing the rest of the circuit. This is the way you will do it in the lab by wiring the circuit. Right. Now we connect the multimeter output terminals to 6 and also the ground point to the ground of the multimeter. So the multimeter is connected, everything is, now I have to connect the voltage source, and you would find I have connect now the voltage source and the ground point of the voltage source. So the wiring has been completed. Now we will switch on the power supply and the voltage source and the multimeter, everything is now ready, and I will select millivolts. So if I increase this, I can increase the millivolt source at input. So I give about 100 millivolt, and you can immediately see the output is 1.1 volt. So if I increase to 200 millivolt, it becomes 2.2 volts. Why is it so? Because R2 is 10K, R1 is 1K, so 1 plus R2 by R1 is 1 plus 10 by 1, which is 11. So 11 times 200 is 2.2 volts, 200 millivolt. So 11 times 300 millivolts is 3.3 volts, etc. So if I keep on increasing, you will see correspondingly the output voltage is also increasing proportionally by the gain factor, right. So having seen that, let us now move on to the table, and I have an actual circuit, the same circuit wired on a breadboard, and I will try to explain to you how this works. So here you can see a multimeter which is connected as at the input terminal, therefore okay, this is connected at the input terminal and it is connected to voltage and DC, right, it is voltage DC, and this is a millivolt source. This is a voltage source where I can change the input voltage using the dials from some 100 millivolt, 200 millivolt to several volts, and that is connected to the input of the amplifier, and I have a dual supply here, and these are the 3 terminals for the plus, minus and the ground. The green one is the ground, red one is the plus VCC, black one is the minus VCC. This is a dual supply, and you also have one more multimeter which is for measuring the output voltage, that is why it is called V output. So you have the circuit here, and to clarify I have given the circuit also here in the circuit diagram. You see here it is exactly the same non-inverting amplifier. The minus input is connected through R1 to the ground, and the R2 is 10K here connected to the output, and this is the voltmeter, and you have the VCC plus minus and the ground connected. This is the voltage source V in that is connected, which is here. So if you look at carefully at the op amp, there is the op amp 741, and you can see the 7 terminal is for the V plus, that is connected to the red wire, and the red wire goes to the plus of the dual supply. And similarly the bottom 4, the pin number 4 is connected to by a small black wire to the negative terminal, and this black wire goes to the negative V minus of the dual supply, and the green wire is actually connected to the ground of the voltage source, and this R1 and R2 are seen, and it is very similar to what you saw on the simulation on the screen. Now if you look at the dial here, I am sure you are able to see that it is about 100 millivolts. This is about 100 millivolts that is obtained from this voltage source. It is connected in parallel to the voltage source at the breadboard, and therefore it reads 100 millivolt. And after amplification you see some number here, I am sure you are able to see that it is 1.13. So the gain is R1 plus 1 plus R2 by R1, that is 11, and therefore 11 times 100 millivolt is 1.1 volt. That is what you are getting here, which is what also we got in the actual simulation. Now let me change the 100 millivolt input by using this dial to 200 millivolt. Now the input voltage is changed to 201 or so, and now let us see what is the output voltage you observe in the V output voltmeter. You would find that shows 2.25, 11 times 200 millivolt. When I now increase the input voltage to 300 millivolts, you can see on the dial it is reading 300 millivolts, and correspondingly at the output voltage you see 3.37 volts. So you may be wondering why I am getting not exactly 3.3, not exactly 11 times, but slightly larger than 11 times. It is 2.25 or 3.37 etc., and that can be very easily explained because this R1 R2 I have assumed to be 1K and 10K. You know there is always a tolerance band, that means the resistance need not be very precisely 1K and 10K, it can be very close to 1K within plus or minus 10% and 10K, and therefore that tolerance variations is a reason for a slightly different voltage that you get at the output. If I choose 1% or 0.1% resistors and put in the circuit, you would find it will be an exact multiplication of 11 and you would get that thing. Otherwise you can actually take these two resistors, measure the resistance value using the multimeter exactly and put that as in the formula 1 plus R2 by R1 and then multiply the input voltage. You would find what you get is exactly the same as what you should get with this multiplication factor. Therefore, this is a very simple effective voltage amplifier. Very small input voltages like 100 millivolt comes out to be 1.1 volt, it is amplified nearly 11 times. If I instead of 10K I have chosen 100K for the feedback resistor, then the gain will be 101 times. So you can by choice of resistors R1 and R2, if I make it 100K it will be 101 times, if I make 50K then it will be 51 times the output. So the gain of the amplifier very easily controlled by simply two resistors, and that way it makes very nice. So if I have a input voltage like from a thermocouple or something, then I will be in a position to amplify that small voltage by using a very simple configuration which is not at all expensive, and with that I will be able to get amplification. You can see what I have done is now with reference to DC, because the operational amplifier can amplify starting from DC, the bandwidth of that starts from 0 frequency up to 1 megahertz for example when you have unity gain. But when you have a gain of 11, automatically the bandwidth will be reduced because the product bandwidth into gain should be a constant. We will discuss this a little later, and we will perhaps take later on an example where I will introduce, instead of a DC I will introduce an AC voltage and vary the frequency and try to measure as we increase the gain how the bandwidth gets decreased. So we will also see that, but for the present we are trying with a DC voltage source and we are measuring the input and the output using multimeters, and you can see by just wiring the very simple circuit with two resistors in the feedback loop you are able to get a very good almost ideal voltage amplifier. And you can also see the sign of the input voltage and the sign of the output voltage are the same. This is also plus and this is also plus, and that means it is a non-inverting amplifier. The output is in phase with the input. If I give plus voltage I also get plus voltage, if I give minus voltage I will get minus voltage, and therefore if I give a sinusoidal voltage I will get another sinusoidal voltage at the output which is in phase without any change in phase, and therefore it is called non-inverting amplifier, and it is very close to an ideal voltage amplifier, and it involves only two resistors in the circuit. So having seen the demonstration, I am sure you would have understood how in a very simple scheme, by just having an operational amplifier which is not very expensive and just couple of resistors which are also very cheap, you can form a amplifier which is a very powerful amplifier, in the sense the gain can be very easily modified. You should compare it with the situation before where you had the transistors. You cannot get this high a gain 11 or 100 or 50 in a moment's notice. By just switching some resistors you are able to get different values of the gain, and you would also observe that the same circuit, if I have to do it with transistors, it is much more complicated because the transistor is a more non-ideal device, whereas an operation amplifier is very close to an ideal device, and therefore you would find the design of the transistor amplifier is much more complicated, and that is why you have to use a H parameter or a R parameter or a Z parameter, and you have to have lot of approximations and then analyze the circuit and then design, and then finally you may find that the design will not lead you to very high gains unless you have multiple stages. Of course, in the operational amplifiers also there are multiple stages, but everything is integrated into a very simple small area of silicon chip, and the gain of the amplifier is 100,000 even when you buy as a one single device. Therefore, by just using couple of resistors externally, you can make any value of gain, and the larger the gain you sacrifice, for example from 100,000 we have come to 10 gain in the example. That means you have sacrificed nearly 10 to the power 4, a gain of 4 orders of magnitude you have decreased in the gain. That will improve the input resistance by 4 orders of magnitude. So your 2 megohm will now become 20,000 megohm. Your output resistance 75 ohms will become 75 divided by 10,000. So every one of the features of the amplifier will be improved by that 10 power 4, which is the value of the gain that you sacrificed. So you find a simple feedback amplifier, negative feedback amplifier, can lead you to a very effective good voltage amplifier by just simple connection with couple of resistors. So we will see in the next lecture about the rest of the feedback configurations, and they also how they lead to a very good close to an ideal current to voltage converter or voltage to current converter or current amplifier. Thank you.